Welcome you all in this new video, and in this video we are going to discuss about the proof of Heisenberg uncertainty principle. Okay, because Heisenberg uncertainty principle is very important principle of quantum mechanics. Okay, and we use this principle to prove that electron exists inside the nucleus or not. Okay, and by this Heisenberg uncertainty principle we can prove that electron is not existed inside the nucleus. Okay, and that is outside the nucleus. Okay, and Heisenberg uncertainty principle is also used to calculate the binding energy of the electron. It is also used to find the minimum energy of harmonic oscillator. Okay, so there is various kind of the application in quantum mechanics of Heisenberg uncertainty principle. Okay, and we know that what is the Heisenberg uncertainty principle? It is that we cannot measure the uncertainty in position and momentum simultaneously. Okay, means what? That is greater than or equal to h cross. Okay, that is equal to h over 2 pi. So in this video we are going to prove the Heisenberg uncertainty principle. Okay, as you see in this picture that this is the I. Okay, this is V, this is observer, and this is the wave character, and this is the position. Okay, so we cannot simultaneously particle nature and wave nature simultaneously observed. Okay, we cannot be able to do this. So this is the experiment through which this was done. Okay, and in this video we are going to prove the Heisenberg uncertainty principle. Okay, that what is that? That is delta x delta p is equal to greater than what? H cross. Okay, that is equal to h over 2 pi. So let's start our video. So first of all, understand what is this Heisenberg uncertainty principle, because in the various component of quantum mechanics we use this thing. Okay, so it simply states that we cannot measure the position and momentum of a particle simultaneously with absolute accuracy. Okay, this is your particle. Okay, either you have two ways. Okay, either you are going to measure the position of this particle accurately, or you are going to accurately measure what? Its momentum. So momentum and position are not going to be simultaneously, okay, with measured with absolute accuracy. Okay, let's start our video. And what we have to prove? We have to prove that Heisenberg uncertainty principle, okay, whose mathematical indication is what? Delta x delta p is greater than or equal to h cross. This is the thing that we have to prove. Okay, where we have to reach. So now the concept is that from which kind of the principle we are going to prove the Heisenberg uncertainty principle. Okay, and this is very important statement, guys. A group of wave, okay, is always associated with the moving particle. By using this principle, okay, what is the statement says? It says that when a particle is moving, okay, there are various kind of the waves that are associated with that. Okay, that is called wave packet. Okay, wave packet means there is no only individual wave. Okay, there is so many waves that are superimposed on each other and form a particular wave, a resultant wave. Okay, that is called wave packet. Okay, and by using this concept, okay, through the de Broglie wave equation, we are going to derive the Heisenberg uncertainty principle. Okay, and this is Heisenberg uncertainty principle can be proved by the de Broglie concept of the wave group. Okay, de Broglie means what? There is always wave associated with the particle. Okay, and what is Heisenberg uncertainty principle that we have to derive? That is delta x delta p is greater than h over 2 pi. You can simply say that is h cross. Okay, so this is the thing that we have to prove. And how we will prove? We will use the de Broglie concept of wave group. Okay, wave group, why we have used wave group? Means there is always the group of wave that is associated with the particular moving particle. Okay, so let's start our video. So let's think that we have two waves. Let y1 and y2 are two waves. Okay, two waves associated with the particle, associated with moving particle. Okay, moving particle. So what is the y1? Y1 will be equal to, we know the what is the equation for a wave. Okay, that is a is the amplitude cos omega t minus kx. These are two waves and these have the angular velocity different. Okay, angular velocity जो difference है that is omega sorry, delta omega, and what is the difference between the waves in this k is propagation constant, okay, propagation constant. Okay, when your wave is propagating in a particular direction, okay, there is a particular constant, okay, that is this k. And what is the difference in propagation wave between these two waves, okay, that is delta k. So our next wave will be y2 is equal to a, okay, cos omega plus delta omega, okay, and t, wait a minute, yeah, delta t, okay, minus k plus delta k x. Okay, these are two waves, okay, these are superimposing on each other and forming a resultant wave, okay. So now we are going to derive the expression for resultant wave, and through that resultant wave, okay, we have to calculate the where is our particle, okay, and where is the position that exists the particle, okay. So what is the resultant wave? That is y equal to y1 plus y2, okay. By combining these two equations we get the final expression for this, okay, that is 2a cos, okay, 2 omega plus delta omega, okay, t minus 2k plus delta k, that is x over 2, and then we have cos delta omega over 2t minus delta k over 2 x. This is the expression that we get by combining these two equations, okay, y1 and y2. So we know that this delta omega is what? This is the angular velocity difference between these two waves, y1 and y2, okay. These are the waves that existed with that moving particle, okay. This delta omega and delta k is very small, okay, as compared to omega and k. So what? So 2 omega plus delta omega becomes nearly equal to 2 omega, okay, this is neglected, okay. And second is 2k plus delta k, this is also neglected, sorry, this k, okay. So this is equal to 2k, okay. So the final expression that we get by putting these values in this expression, okay, so that is 2a cos delta omega over t, sorry, 2t minus delta k over 2x, okay, cos omega t minus kx, okay. This is the expression that we get for the resultant wave, okay, that is we can say wave packet, okay. What is the expression? Y equal to 2a cos delta omega over t, sorry, 2t minus delta k over 2k, sorry, x, okay, cos cos omega t minus kx. This is the expression for that. Now understand what does this equation means, okay. This equation says that there is a wave, okay, which the angular velocity is this, okay, angular velocity, there is a wave, okay, like this, and what, which have the angular velocity omega and wave function or wave number, that is propagation constant k, okay, and that is superimposing on another wave, okay. Another wave means there is another wave like this, okay. There is another wave whose angular velocity is what? Delta omega over t, and what is the wave number? That is delta k over 2, okay. Means this is, and these two are the two waves, okay, and these are superimposing on each other, and this is the final expression for a wave packet, okay. So what this is, understand, so this is the expression that we get, okay. Let this is our axis in which we are getting, and this, okay, this, and these are, you know, overlapping with each other. So and this kind of the arrangement that we get, okay. So now what is the expression that we had get, okay, y equal to 2a cos delta omega over 2t minus delta k over 2x, okay, cos omega t minus kx. So this is the expression that we have. Okay, so what we are going to do, we are now we have this resultant wave. Okay, now we have to derive, we have to calculate or measure where is the particle, okay, in this wave. So let these are the consecutive nodes. Okay, consecutive nodes means there a point where it is superimposing with each other. Okay, let this point is x1 and this point is x2. Okay, these are two consecutive nodes. Okay, so what we know, that the particle will be somewhere between these 2 points, okay, x1 and x2. So what there is formation of node. Okay, formation of node. What is the condition for the formation of node? That is, your amplitude should be 0. Okay, what is the amplitude here? Here is the amplitude, this 2a cos, let me change the color, this part. Okay, this part is our amplitude of this resultant of wave pocket. Okay, wave packet. So this will be equal to 0 for the formation of node, because there is the formation of nodes. So by the formation of nodes, we comes to know that these are the ranges within which the particle can be, okay, in a particular wave. Okay, so what so this will be equal to 0, so this will become cos, we are putting this equal to 0, cos delta omega over 2t minus delta k over 2x equal to 0. Okay, so when delta omega over t, okay, minus delta k over 2x equal to, so this will be pi over 2 by this 2n plus 1, okay, pi over 2, because cos 90 is 0. Okay, so that's why we do this thing. This is the simple mathematics that we use. Okay, so finally we get delta omega t minus delta kx equal to 2n plus 1 pi. Okay, so now see, this is the expression that we get. Okay, so now we have to put the values of x1 and x2. Okay, x1 and x2 are two consecutive nodes. Consecutive means one after the another. Okay, so this is first one, this is the second one. So first one we have to put x here. Okay, x1, so this will be for x1 and x2 nodes. Okay, for x1 and x2, wait a minute, for x1 and x2, okay, put the x1 in this expression, so we will get delta omega t minus delta k x1, okay, is equal to 2n plus 1 phi. Okay, now second one is we have for x2, that is omega, sorry, delta omega, wait a minute, delta omega t minus delta k x2. Okay, so this is equal to 2n plus 3, because these are consecutive nodes. Okay, consecutive means one after the another, so we are using this. Okay, by subtracting, let this equation say x equation. Okay, this is the y equation. Now subtracting y equation, okay, like this, x equation is subtracted by the y equation, so final expression that we get by this, okay, that is delta k x1 minus x2 is equal to 2 pi. Okay, so x1 minus x2 is equal to 2 pi over delta k. Okay, so now understand what is this. This is, we can say this is delta x. Okay, because the difference between two values or consecutive values is always in the form of delta. Okay, so what is the k? Delta k, k value is 2 pi over lambda. This is the value and this is the expression for k, propagation constant, that we already know. Okay, so from here we can easily calculate the value of delta k, so that will be equal to what? So from here we are using de Broglie wave equation. That's why in the earlier of this derivation I told you that we will use the de Broglie equation. Okay, that is lambda equal to h over p. So this will be 2 pi over h dp. Okay, by we are using placing this value in this. Okay, so we get 2 pi, okay, over 2 pi dp h. Okay, by cancelling 2 pi, so dx is equal to h over dp. Okay, this is the expression that we get. Okay, so now excuse me, सॉरी, देखिए अब देखिए ये एक्सप्रेशन हमारे पास आया है एंड वी विल यूज दिस एक्सप्रेशन लाइक दिस. ओके, व्हाट डेल्टा एक्स प्रोडक्ट ऑफ विद डेल्टा पी. ओके, वेट अ मिनट, we will use delta x and delta p is equal to h. Okay, and more sophisticated approach for this will be, we will do this delta x and delta p is equal to or greater than h cross. Okay, this h cross. So this is the proof for Heisenberg uncertainty principle. Okay, and this is very simple and a very important concept of quantum mechanics. Okay, so understand by first. So what we did, okay, let me explain what we did. Okay, we did first of all what we used two waves. Okay, y1 and y2. We combine these wave and we get a final wave represented y. Okay, and by using this wave, what we did, we did the amplitude of this wave, we take that 0. Okay, why? There is a formation of node. Okay, when we put this value equal to 0, we get the value of delta x. Okay, from the delta x value we also get the value of delta p, and by the doing further this expression, okay, we finally reach at our destination, that is Heisenberg uncertainty mathematical expression, that is this. Okay, I hope you like this video. If you like our video, then give a thumbs up. Thank you so much. Wait a minute.